with questions from homework? Does anyone have questions from homework?
I do, but can I just submit this, please?
Uh-huh.
Okay.
Anyone else with homework questions while Chanel's kind of cleaning stuff up? Yep.
I have to get on that real quick.
Sure.
So number 35. I was confused because I checked the answer and I had it almost right, but there was an extra piece in it.
Okay.
I didn't do anything with the greater than T or less than T thing, so I thought that might have been possible.
I don't think that should matter.
Okay.
So the antiderivative cosine should be, or cosine, the antiderivative cosine t is
Sine.
sine t. And the antiderivative secant squared t is
Tangent?
tangent t.
Wait, is it sine T? Is it negative sine?
Nope. Right, because the derivative of sine is cosine,
Yeah.
right? And then I have a plus c at the end. And then we want to check, so we know that if I plug pi over 3 in, oops. I should get 4, right? Now, pi over 3 is 60 degrees. So that's going to be the big value for sine. That's root 3 over 2. Tangent of pi over 3 is going to be y over x, so just root 3. So we end up with root 3 plus root 3 plus c. So c should be 4 minus 2 root 3.
Oh, yeah, I know what it is.
Oh. It's always reassuring, isn't it? So that should be our final, I think. Is that okay?
Yeah.
Okay, Chanel, you said you had one too?
Yeah, it's actually 37 from 4.8.
4.8, 37. You said 37?
37, yeah. It's the very last problem, actually.
Okay. It says use Newton's method to find the coordinates of the inflection point of the curve. Y equals x squared sine x from 0 to pi, correct to 6 decimal places. So the inflection point comes from
Concavity.
setting the second derivative equal to 0. So my first step would be to calculate the second derivative. To do that, I'm going to need to do a product rule for the first derivative, and the second derivative is also going to be 2 product rules here. So x squared negative sine x plus 2x cos x plus 2 sine x plus 2x cosine x. And I'm going to set that equal to 0. So I have negative x squared sine x plus 4x cosine x plus 2 sine x equal to 0. So that's what I'm going to be doing my Newton's method on. So Newton's method requires the derivative of this equation, right? This is like my f of x. So I'll take the derivative of this guy now. Oh, Mr. Kulak.
Wait, why would you take the derivative of this?
To use Newton's method,
Okay.
right? Which is like, I know that Newton's method is like xn equals xn minus 1 minus f of xn minus 1 divided by f prime of xn minus 1, right?
27?
37
Oh.
from section.
Oh, I'm thinking of another. I was thinking of 4.9 for some reason.
Okay,
So.
that's okay. So I'm going to calculate my derivative here again, which again, a bunch of product rules, which is just like, come on, but it's okay. They're not hard product rules.
Yeah, it got very messy here.
Yeah. So I think that'll do it. And now it's just going to be calculator time. So we'll have negative x squared sine x plus 4x cosine x plus 2 sine x, and then negative 2x minus x squared cosine x plus what? Oh, what did I type in? Oh, yeah, thank you. Yeah, good. Good. All right, negative 2 sine x. And cosine square, okay, plus, we have 4 cosine x minus 4x sine x plus 2 cosine x. And I know I could have combined some like terms here, but just didn't bother with it. I need a guess. I'm just going to use 1. I don't know. And then I'm going to do ants minus vars, y vars, function y1 of ants divided by vars, y vars, function y2 of ants. And then I'm just gonna, oh, this doesn't look like it's working at all. Well, I made some kind of mistake here. Anybody see it?
I mean,
I-
they're not the same thing, so.
I ripped through that kind of quickly. I'm sorry about that also. Probably made it hard to follow. This is 4.8, right, that we're looking at? Let's see. What did we do wrong? Probably a Mr. Kulik mistake. All right. So I have the correct thing. Okay. Well, let's do this. I'm going to turn these off real quick. And let's just graph this original guy, x squared sine x. And let's look at it from 0 to pi. That's probably good enough. Oops, I'm in degree mode. That's not right. Oh, that's probably why I got the wrong answer, though. That did it right there, I'm sure. Oops, it's not tall enough. Just a little bit too, not tall enough. Let's make that 6 or something. All right, so if I look at this real quick, the change in concavity looks like it's somewhere around here, right? So maybe I'd pick like 1.5 as a guess, but I think 1 should have worked if I hadn't been in, yeah, there we go. So that worked still. If I hadn't been in stupid degree mode, should have come up with that one real quick. I'm glad I did that right, though. All of the setup was correct. It just, the mode of my calculator. Oh, Mr. Kulik. Pierce, you said you had one?
We did 4.9 as most recent.
Yep.
4.930. Wait, I think it's 33.
33. Okay. So when I look at this, I'm going to think about this as 4 times 1 over 1 plus t squared. Why would I think about it that way? Inverse tangent, right.
Oh, that's right.
Yeah.
I was extremely confused.
Yep. Excellent. And then from here, it's just plugging in, right?
Okay. Yeah, I did the separation with the 4 and the 1 over.
Good.
1 over that. I just was not understanding how they started getting all that stuff. Thank you.
Yep. And tangent inverse of 1 is pi over 4. So C is negative pi, I think. Chanel?
All right, number 71.
It says a company estimates the marginal cost in dollars per item. Dollars per item, what is a marginal cost then? If it's a rate, it's a derivative. If it's something per something, right? So all derivatives are rates. Of producing X items is 1.92 minus yada, yada, yada. If the cost of producing one item is $562, what is the cost of producing 100 items? Well, I'm going to take my antiderivative.
Oh, I thought it was just like, that was the rate. You just plug it in.
Yep. And then we'll plug in to solve for C. And then whatever that value is, we just, that gives us our C of X, and we just do C of 100 then with our C that we just would solve for. Does that feel okay? So again, the key here was recognizing that this marginal cost, because it was a rate, was the derivative of the cost, right? This is why most schools, if you're studying economics, require a calculus course, because these marginal costs are derivatives of your cost function, which is pretty neat. Yeah, Chanel?
77.
Yeah.
I just have a question about those.
What's up?
So those that equation that you get, that they're giving you, like in real life, how would you get that sort of thing?
Well, you'd probably have started with a cost function, right? Well, I mean, again, a marginal cost you could just compute empirically. You can look at your business operation, be like, oh, it cost us, 54 million, dollars to produce, 13,742 items. The cost per item is, like you'd probably have done that empirically. Or you'd have had like a fancy computer model, like where you're like, okay, we spend this much on this stuff and we spend that much on that stuff, and we're going to produce things at this rate, and like it would be done computationally or whatever. But I think, again, I'm not a like business optimization expert, but I suspect that that's probably where you start. Okay, a car is traveling at 100 kilometers per hour. So that's our start, right? So that's V of 0. When it sees an accident, 80 meters ahead and slams on the brakes. What constant of deceleration is required to stop the car in time to avoid the pileup? So I need to find S of t equal to, I'm going to call that S of t1, has to equal 80, and then V of t1 has to equal 0, right? And we want to find this A of t. Does that sound about right about what we're looking for? Okay. So I'm going to say A of t is equal to just some constant. I'm going to call it c for now. The derivative or the antiderivative of that should be velocity. So that's going to be cx, and I'll call that plus d. I know that v of 0 should be equal to 100. So I can see that d is going to be 100. I'm going to call this cap A for acceleration. I'm going to get confused here. If I call it A, that'll make much more sense to me later, that A is my acceleration. Is everybody okay there? Okay, and then we'll do the antiderivative of that. So that's going to be A times x squared over 2 plus 100x. I should be using t's, Mr. Kulik. You bozo. That's fine. Plus c. And then I know that S of, okay, and then we need to solve V of t equal to 0, right? So let's find that specific value of t. So if I do that, I get that t equals negative 100 over a. Everybody agree with that? Now, clearly a is going to be negative because the time here has to be positive, but I'm just going to leave it as a, and just the negative will show up when it does. So I know that S of negative 100 over a should equal 80, right? Because that's the time it takes the velocity to go to 0. That means the car should just go 80 meters. So I can stop in time. So we can say 80 equals a over 2 times negative 100 over a squared plus 100 over, or times negative 100 over a plus c. And ooh, that c. What am I doing with that c? Can I just let that be 0?
Sure.
I'm trying to think. Yeah, I think that's what that means, is that has to equal, this has to be, I think that's what I'm going to have to say. That's what I want. Is I want this to be 80. The c should be 80. because then I want this to be 0, right? That we're at position 0, and this is 80, I think. And now we're just solving for A. Let me double check back here to make sure I did that right. But I think that should be right. This is, that's the wrong section. It's like, oh, it has a picture of a weird triangle thing. I was in the wrong section. It's like, that's a bad sign. Okay, so that they agree with our time. If 0 is 100. So you have KT times 100. Okay. It's going to be, yeah, 1/2. Okay. I got that. And then that. So I said that. Okay. Yes. So they're just saying this, right? So they're doing that. So if I do that, I get, what do I have? I have 2, 3, 4. Oops. Divide by 2 over A, and then minus 1, 2, 3, 4 over A. So if I do that, that's oh, yeah, so that's negative 5,000 over A. And, oh, there we go. And this value then has to be less than 80 meters. Notice that these were kphs. So I'm just going to call that, if I divide it by 1,000, now it's in kilometers. And I'm just solving for A. Does that make sense? Maybe until the very end, where it got a little sketchy. Talika's like, I don't have any of it.
Yeah.
You missed 2 days. It was a lot. All right. So I'm going to start 5.1 here. Won't finish 5.1 because we spent more time than I thought dealing with questions, which is fine. First hour didn't ask any. And we finished on time for them. We'll catch up the next day. It's not that big of a deal. We'll find a chance to get everybody caught up.
Sorry.
It's not your fault. Just like, you know, like being honest with kind of where things are at. All right. So section 5.1 is about area and distances, and somehow this is going to be related to this anti-differentiation process, which seems weird. So let's kind of show you kind of why. So let's say we have a function s of t that gives you some distance in meters. We have some velocity function that gives you distance or velocities in meters per second. Let's just say that we have our velocity function is a constant function. It's just 10 meters per second. If I draw a graph of this, we have a v of t axis, and here at 10 meters per second, it's just a straight line, right? If I'm interested in how far we go in, say, 3 seconds, I can do my antiderivative and just assume that if I'm asking how far we go, that's a displacement. So even if I have to tack a plus c, it's going to be like 0 plus c, or, like 3 times 10 plus c minus 0 plus c. So the c's are just going to cancel out. So I'm just going to ignore them. No?
Yeah.
No? It's okay? Okay. So if I do s of 3, that's going to be just like 30 meters, right? If I build a rectangle here at t equals 3, the area under that curve is 30 also, right? And the units should make sense because the height of the curve is 10 meters per second times 3 seconds. So the seconds cancel and you're left with just meters also, right? So somehow this area under a curve is intuitively related to this anti-differentiation process, right? Now that we just a little like trivial example, we can kind of see why we're interested in this maybe. So we're going to tie this together here inside of the next couple of sections. But here in this section, we're only going to be interested in how do we calculate these areas under curves? Because not all the time are we going to have something that looks like a polygon. What if we have something that looks like this? Pretty rough, right? It's not a polygon. It's not like I can decompose this into like, pieces of circles and rectangles and triangles and stuff and like geometry it together. The squiggly part is just like, it's a squiggly part. It's a curve. How do I do this? So this is the idea. Let's back up a skosh to something a little bit simpler looking. We'll just look at the function y equals x squared. And we're just going to consider this from 0 to 1. So I'm just looking at the area under the curve, y equals x squared, from 0 to 1. Now, intuitively, right away, I can tell that area is bounded between 0. Obviously, it's bigger than 0 because there's an area here. I can see it. And if I think about this square, it's a 1 by 1 square. So the area that I'm looking for has to be somewhere between 0 and 1. Everybody can see that. That's kind of trivial to say, but that's what we're going to do is we're going to try to like upper and lower bound this tighter and tighter and tighter until we like sandwich it together, which should sound familiar. It's a little squeeze theorem-y. Okay. So what we're going to do to this is we're going to chunk it, just like you would do in a geometry problem. If you have like a complicated looking polygon, well, I'm just going to divide that up into like rectangles and triangles and stuff until I can piece it together. So we're going to do the same idea here. We're going to chunk it up into 4 pieces here. I used the distance between my 4 pieces to be the same. So far, so good. Now, I still can't calculate the area of any of these pieces, but they're starting to look a little bit more geometric, right? So let's now shoot for a better upper and lower bound. So if I say make a rectangle whose base is the x-axis on these subdivisions, and its height is, say, the value of the function at the rightmost part of the subdivision, and I make a rectangle. Oh, that's not at all. I don't know how I did that. I can do something like this, right? Is that going to be, is that area of those rectangles, that's something I can calculate easily, right? Is that going to be an overestimate or an underestimate?
Overestimate.
Overestimate. What if I do the same idea, but this time I use the left end of my interval? So the first rectangle is there. The second rectangle would be there. The third rectangle would be there. And then the fourth rectangle would be there. That one's going to be an underestimate. So I found a new, better bound, right? So I'm going to call the red ones R because I'm using the right hand end of the interval. So that was 1/4 times f of 1/4 plus 1/4 times f of 1/2. In fact, I'm gonna cut that 1/2 or the f of. I'm just going to use x squared, right? Because that's what we're using. That's our f. Chanel, what's up?
Wait, so where are you getting these? Are you just like where are you getting these 1/4 times like all of these numbers from? Like,
So how far is this? That's the width of our rectangle, right?
1/4.
It's 1/4. And what's the height of our rectangle? It's going to be 1/4 squared because it's the function is y equals f of x or y equals x squared.
So are you taking R and subtracting it from the two?
Nope.
Okay.
I'm not doing any subtraction here. I'm just kind of writing down intuitively like what these two different sums would be. Everybody's okay with that? And I'll call this R4 and L4 because I have 4 subdivisions here. How could I get a more accurate estimate than this? I sure can.
Into smaller chunks.
Break them into smaller chunks. Use more rectangles. So to get the exact area, I'll use infinitely many rectangles. And at that point, the value of L4 or Ln should converge to the value of Rn, which should both be the area that we're searching for here. Is everybody okay with that notion? This feels very like first chapter-y, right? Where we're using infinite number of things. This idea here will be repeated over and over and over again this semester. So if you want to find the accumulation of something, we're just going to break it into infinitely many parts and add up those parts. That's the idea. So here's our overestimate. And there's our underestimate. I did this all in just one spot. And here's if we do more rectangles, we're getting a better over and underestimate. And if we use infinitely many rectangles, let's see what we get here. So we're using this from the right sides. So my subdivision is 1 over n, because I'm taking 1, 0 to 1. I'm splitting into n chunks. And then I'm going to have 1 over n squared, because again, it's x squared. That's the height of it. And then I'll have another 1 over n. But now I'm at the next spot, which is 1 over n plus 1 over n, or 2 over n. And we'll just kind of keep doing this. All the way out, right? It's just the second to last subdivision, right? There's n subdivisions, so the second to last one is n minus 1. The last one is n. If I look here, I notice that each of these terms has a factor of 1 over n. So I'm going to pull that out front. And each of these factors has each of these terms has another factor of 1 over n squared. So I'll pull that out front. And what that leaves me with then is a 1 squared plus 2 squared plus yada, 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 n minus 1 squared plus n squared.
So where'd you get the n minus 1 and the n? For the third and fourth.
They're not the third and fourth one. That's see the ellipsis in the middle? That's the n minus 1th one and the nth one. That's why there's n minus 1 and n. So like I did, I have the first rectangle, second rectangle, dot, 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 last rectangle, second to last rectangle, and last rectangle.
So wait, so because they're on top now, the rectangles, now you're starting to subtract?
I have done no subtraction anywhere.
Like, is it because the rectangles are now on top that you put n minus 1 squared plus n squared?
No.
Oh.
So this is like the first rectangle. That's the second rectangle. Dot, dot, dot. This is like the n minus 1th rectangle and the nth rectangle. Right? We're doing this arbitrarily. We've split it into n subdivisions. So we have like the first one, the second one, the third one, the fourth one, the fifth one, all the way out to like
Oh, I get it.
n minus 1 and then the nth one, right?
Got it.
Okay?
Thank you.
Uh-huh. Yes.
All that highlighted stuff that you have there, that after the dot, 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 is that plus or minus?
No, that's just a plus.
Okay.
Now, this piece here, maybe you remember from your Algebra 2 class. Oops. Does anybody recognize that? The sum of squares?
Yeah.
That was n times n minus 1 times 2n plus 1, I think, over 6. I have to look that up real quick. It's not important that you'd have that memorized. I would not expect you to have the, oops, they're both plus. Would not expect you to have that memorized, as obviously I didn't have it memorized because I had to go back and look it up. So what we have here then is like Rn is equal to this. So if I wanted to do the area, that should be the limit as n approaches infinity of Rn, which is the limit as n approaches infinity of 1 over n. Well, let's see, we can do a little reduce here, right? Squared, well, that's 6n squared on the bottom. And then n plus 1 times 2n plus 1. Is everybody okay with how I got to there? That's a limit you should be able to do in your head. Nope. You don't need to do L'Hopital. You can just use a polynomial. The degree of the numerator is 2, because it's a degree 1 polynomial times another degree 1 polynomial. The leading coefficient of the numerator is 2. 1n times 2n would give you 2n squared. The degree of the denominator is n squared. The leading coefficient in the denominator is 6. So the limit should just be 2 over 6 or 1/3. That is our area under the curve. We did it! Pierce.
Sorry. Where you have that sum of, you have n on the top of sum of bottom.
I equals 1.
And then what's on the right?
I squared.
Oh,
Chanel.
Where did you get this n times n plus this whole thing? Like n times n plus 1, 2, n plus 1 over 6.
That is what this sum is equal to. We remembered that from Algebra 2. I would not expect you to have that memorized.
Oh, okay, and then, so why did you set that equal to that? Like,
This
X
is equal to this.
okay,
That's what we had said.
and then and then you're just looking for the limit as n approaches infinity because it's, okay, and then how'd you get the 1/3?
I did, this is a polynomial.
Okay,
Its leading term is 2n squared. The bottom is a polynomial. Its leading term is 6n squared. Since the degrees are equal, the limit is going to be leading coefficient over leading coefficient, 2 over 3 or 1/3. Or 2 over 6 or 1/3, excuse me. Okay. If we did the same thing for L, what's going to happen?
Same thing.
We get the exact same answer, right? I'm not going to go through the details because, woo, there's a lot of details. Now, we can do this generally for any curve. It doesn't have to be specifically y equals x squared. We picked that one because this we conceivably knew how to do. That's the hard part of doing this. And it's the part we're going to get rid of real quick, but we're going to pretend like we aren't going to get rid of it for a chapter or two, so we can see like foundationally what this process is doing. But we're going to shortcut through that part real quick. So let's just say we have some arbitrary y equals f of x. Again, what we're going to want to do is we're going to chunk that up, and let's say we're looking from a to b. Right, the area under some curve y equals f of x from a to b. We'll chunk that up into n pieces. We want to chunk it up into n equal pieces. So to do that, we're going to take the distance from a to b and divide it from n, or divide it by n. We're going to call that distance delta x. So this formula you're going to use every single time. Everybody's okay with that? Now, to figure out what each one of these endpoints is for our subintervals, we know that the first delta, or the first value, should be a plus delta x, right? And then to get to x2, we went another delta x, so it should be a plus 2 delta x. And then the x3 should be a plus 3 delta x. xi should be a plus I delta x. xn should be a plus n delta x's. Everybody's okay there? So we do that. So our formula for Rn would just be f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x all the way out to f of xn times delta x. Or really, f of a plus 1 delta x times delta x, plus f of a plus 2 delta x times delta x, plus f of a plus I delta x times delta x, plus f of a plus n delta x, or if we sum that together, there's a delta x in everything, times the sum from I equals 1 to n of f of a plus I delta x. Shall?
why don't you specifically pick f of a plus I delta x?
Well, I indexed it with a variable. So whatever the variable is that I'm choosing to use as my index variable should be in my formula, right? So just like I is going from 1 to n, so it's f of a plus 1 delta x times delta x plus, and then I goes to 2, f of a plus 2 delta x times delta x, and then a goes to 3, or I goes to 3, and I just keep going, right, all the way to n. So it's the same formula as above. It's just compacting it into a sum, so I don't have to write all that mumbo jumbo down. So here again is like my estimate. And as we've stated previously, our first definition, the area of region S that lies under the graph of a continuous function of f is the limit of the sum of the areas approximated, or the areas of the approximating rectangles, which is just exactly what we've been writing down the whole time. And you could show it works either using right hands or left hands. It doesn't matter. Everybody's okay there? And in fact, let's skip through that. Oh, where's that? Where's that spot? Did I skip through all of that, or did I do that? Sorry, guys. Don't look at this. You're going to get car sick. I always do when people are like moving screens up and down on me. I'm like, oh my God, I'm going to be sick. No, I don't know. I lost it. Okay, whatever. It's fine. So in general here, we can do even better than this, because these values in these definitions, these x1s, x2s, xn's, etc., don't even have to be the endpoints of our subintervals. If we're doing this infinitely small, we can really do like just do this one. We can use any value where xi star is anything on the interval from oops, that should be the other way around. Anything on that subinterval. So like x1 star is any x value from a to x1. x2 star is any x value from x1 to x2, right? As long as it's in there, that's fine. Any sample point will work, particularly if you're taking infinitely many of these things. So like if they get infinitely thin, doesn't matter the x value that you pick on them, you'll end up with the same result. It doesn't have to be a left or a right. It could be anything in between, and it's fine. Shina.
I don't get it. I'm sorry. I don't get what you just wrote.
So we had this thing, right? And before we had been like building our rectangles like this, right?
Yeah.
What we're saying here is you don't have to do that. I can pick like this value here, and then I could pick that value there. Oops. Or I could pick like this value here. Doesn't matter where I pick the x value. It doesn't have to be the start or end of one of these subintervals. Be something in the middle, and it'll still work. That's all we're saying.
Okay. So
Now in practice, you're not going to do that.
Okay.
But we're just showing you that because we're taking infinitely many of these rectangles and these subintervals are getting infinitely thin, the value you pick from the subinterval to find the height of your rectangle doesn't matter.
So what was the difference between this and then the blue rectangles you just drew?
Because before we were always using like either the start or the end of the subinterval.
Okay. Now you're saying any point.
Any point in the middle is fine.
So what does the notation say then? Like what are you saying in the notation? Like,
That's what the star, xi star means.
so like any point in between those two endpoints.
Mm-hmm.
And then so what does this big like backwards Z kind of
That's the summation notation. It stands for just a sum.
So sum of what though? Like sum of all of those.
Sum of the terms f of x times delta x. So these are the heights, and those are like the widths of our rectangles. So each rectangle for I equals 1 to n, just a height times a width.
Okay, sorry.
Is that
I
okay?
just had to take a minute.
That's okay. Braden.
So basically,
what we're seeing is if you take infinitely many of them, it doesn't matter if you do a left bound or a right bound or a middle bound or some other height, you get the same answer. They're all the same. That's what we're saying here. So yes, as long as you're taking infinitely many rectangles, it doesn't matter where you're pulling the height for your rectangle from, it's going to work.
And one more question. Apart from earlier, where we wanted like n times in a prop, like what when they're giving you the information, how would you know what n is?
It'll tell you. So just do an approximation where you get like n is 4 or n is 10. And then it's just like you're building 4 rectangles and adding them up. You know, like it's the actual meat of doing this in this section is going to be pretty straightforward because all you're doing is finding the areas of rectangles and adding them up. Like the algebra is not going to be tremendous. Like the vocabulary and the notation will be a little bit of a headache, but like the actual arithmetic that you're going to be doing is going to be pretty straightforward. Let's do this example, and I think we'll kind of bring it home here. All right. Using the right endpoint, find the expression for a as a limit. Do not evaluate the limit. Okay? So the area is going to equal the limit as n approaches infinity of Rn. That's right endpoints. So that's the limit as n approaches infinity of the sum from I equals 1 to n of, let's plug that in. We'll do e to the negative xi, because our function for f of x is that, delta x. Now, I can do a little bit better than this, because I know if we're going from 0 to 2, my delta x is 2 minus 0 over n, or 2 over n. And my xi is going to be a plus I delta x, or 0 plus I times 2 over n. So there's my area expressed as a limit. Is everybody okay with how I filled that in? Basically just use my formulas, right? And then to do part B, I'm just going to do this for 4 because, well, time, we have 2 minutes. So R4, well, I'm going to have 2 over 4
Good afternoon, Notre Dame Press.
times,
Let us end this day
oh, let's
in
do
prayer.
this first.
In the name of the Father, and of the Son, and of the Holy Spirit, amen. We will be the happiest people in the world if we belong to God, if we place ourselves at His disposal, if we let Him use us as He pleases. To be this happy, we must belong to Jesus fully, without reservation. He alone is worthy of our love and our total surrender. Once we really belong to Him, then He is free to use us, to do with us whatever He pleases. Amen. Just a quick
2
announcement
minutes.
as we end our day today. The cross-country meetup this afternoon in Rochester is canceled due to weather. That is all I have for today. Have a safe afternoon, students. If you're driving, please be safe driving home, and take care of each other. Have a good rest of your day.
That's the A in our problem because we go from 0 to 2, right? The problem says 0 to 2, so this is like my A and that's like my B.
Shouldn't the 2 minus 0 over 4 count?
That's the delta x. Hold on, guys. So R4 is going to be e to the negative 1/2 times delta x 1/2. And then we'll have e to the negative 1 times delta x. And then e to the negative 3/2 times delta x plus e to the negative 2 times delta x. Because again, this is x1, x2, x3, x4. We've just plugged them in to our f of x.
Wait, so the
And then it's calculator time.
no, I literally wait. So the 2 minus 0 over 4 is the 2 over n equation. Like,
So, Chanel, delta x we defined as b minus a over n.
is that part of the equation? Like,
That is always the same.
Thank you, Mr.
oh, okay, got it.
That is always how we find delta x.
Is it really in there or just that?
Yes. And the first 6 are the bold ones.
Okay, oh, thank you. Oh, so there's a homework quiz, like these questions. Oh, okay.
Alright.
This is something you absolutely will, they'll ask you to do on the AP exam.
Oh,
It's to calculate the area under a curve using these rectangles, using the left hand, right hand, or midpoint rules.
okay, thank you.
You're welcome.
Are 4A and 4 on our next test?
Yes. Yes. You're welcome.
Have a nice day.
You too. Phew, motored that.